Okay class, so in the last video we learned the problem of using affine texture mapping with a perspective system. So let's learn how to fix it. Let's learn about perspective correct texture mapping. And the solution is actually quite nice. It's a bit tricky, so don't go to sleep on me here, but it's actually quite a nice solution. What we want to do is we perspective correct those texture coordinates, the u's and v's. Okay, before we interpolate. Right, so what ends up happening is we interpolate in this, I'm going to call it divided by z space. Right? Everything's divided by z. It's all perspective projected. Now we can do linear again in the projected space. We can do that. We can do linear within that space. And then once we do that, because we don't want to have to redo all of our textures and reproject all of our textures too, we multiply back by z. To bring it back. So remember, let's see if I can draw this out. This is my object coordinate space. When we do this, we create vertice 1, and we give it, if you recall, a u value and a v value. I'm going to call that u1 and v1. And then down here we have a vertice 2. I'm going to give it a u2 value and a v2 value. And over here we have a vertex 3. We give it a u3 value and a v3 value. Now this is all in object space. It's not been projected. And over here I'm going to draw this triangle. This is some projected version of our triangle. This is on viewport. I'll put in brackets here. It's been projected in a non-affine fashion. Now, of course, we know that this is V1, this is V2, this is V3. But now we have some additional information. We know it's V1, and we know that it's been divided by Z1. And V2, well, we know that one's been divided by Z2, and V3 has been divided by Z3. Okay. So what do we do then? How do we bring these two together? We have a projected one on the right, and we have an unprojected one on the left. We create a new triangle, at least conceptually. And in here, what we do is, well, we already have this projected triangle. We calculate u1 over z1. Okay. We have the z1 from over here. I'm going to highlight it. We have the z1, and I use it here. Right? We calculate u1 over z1 at that corner. So we perspective project that vertice. We do the same thing for v1. We divide that by z1. And in addition, I'm actually going to work, and you'll see why a little later. I'm going to calculate 1 over z1. I'm going to divide 1 by z1 because I'm going to need that information later. We'll come back to that. Now that's not enough. I need to do it at every vertice. So down here, I do u2. Now be careful, I divide this by z2. Right? I divide this by z2 here. And I do the same thing for v2 over z2, and I also do 1 over z2. I calculate that, and let's finish it up. The last one is u3 over z3, v3 over z3, and then 1 over z3. So what I've done is I've taken my texture coordinates that I've previously only specified in object space, and I've kind of moved them into the screen space by perspective projecting them, okay? Kind of. They're not translated the same way, but they're going to get that same convergence and the same non-affine thing happen to them. Okay, so now what do I do? Now what do I do, right? So first I'm going to write out what I said. Let's calculate un divided by zn for vertice n, vn divided by zn for each vertex. This generalizes to a quad as well, but again, we don't really deal with those. we want to also calculate 1 over Zn. Yeah, because we need it later, trust me. Okay, now we have those coordinated, calculated. Now it gets interesting. If I have a point, I'm doing my rasterization over here. I have a point P. We already know that I can use my barycentric coordinates here to, I can calculate this in terms of barycentric coordinates, and I can move that to this triangle here. Okay, it's the same triangle. But now, instead of using the u's and v's for my unprojected space, now I use my u and v's as, not, let's fix that. I use my u and v's for my projected space. So what I do is I'm going to use those. I'm going to interpolate those projected. Projected might be a strong word. Those, I'm going to say perspective corrected. U, V, and Z values. We have N, right? 1, 2, and 3 of them. I interpolate those to get this interpolated U and V. So I'm going to get U, I for interpolated. I'm going to get V, I for interpolated. And I'm also going to get 1 over Z, I, right? Okay, I'll just write it like that. So this is just coming back to my barycentric coordinates. We've been doing this already in a class with color. Now I'm just doing it on my perspective corrected U, V, and my 1 over Z, which we'll use later. Previously, in the affine one, I would do it in object space. So I'd barycentric interpolate my standard V's and U's, so U's and V's, and that's why we'd have a mismatch. We'd have this perspective projected, perspective corrected raster space, this not perspective corrected object space, and they mismatched. Now I've brought my texture coordinates, U's and V's, into my perspective projected space. I interpolate those, and I'm going to get new U and V values that represent, because now it's linear, because we're in the same space, I can use this linear interpolation. We use those, so that's good. Now, unfortunately, we can't use those in our S&T. We can't use it in our texture space because we've divided by Z. Like, it's a different coordinate system now. We've done this perspective correction, so we can't use those directly. But we can now calculate those at each point as we rasterize the triangle. So let's look at step 3. Okay, we can correct these back into the space that we can use for our textures simply with a division, multiplication. So we get corrected U and V by multiplying back by Z. Except we don't, which Z do we use? We're in the middle of the triangle, right? We're in the middle of the triangle. Do I use the Z from vertice 1, Z from vertice 2? Which one do I use? Oh wait, Jim, you've been interpolating Z as we go. We've been interpolating Z as we go. Awesome. So I've been interpolating that divide by Z, so I use that to multiply back. So I want to multiply back by Z. Oops. And this is how I do it. First, I find my Z that's interpolated by simply 1 over Z interpolated. Now this actually confuses people for good reason. People look at this and go, why don't you just say Zi? Well, we've been interpolating the 1 over Z's, right? We were interpolating those. So now to bring it back, we have to invert it again, or if we take the reciprocal again. So we went over again. And that'll give us our Z that's interpolated. Now that we have the interpolated actual Z coordinate, then we can calculate our U corrected equals U that's interpolated times our Z. And then our V corrected can be our V interpolated multiplied by RZ. And online, you'll see this written as like, oh, UC or U equals U times 1 over Z 1 over something like that. You see these funny notations online. I always find them confusing. I like it much. This seems like a lot more sense to me. Okay, instead of going U times Z over 1 over Z. Blah. I don't know. So we just do this corrected. Oh, I know what we'll see. We'll see UI over Z times Z, and they go, see, but you're dividing by Z at the corner and you're multiplying by the interpolated Z. So forget what you see online. This is the way to do it. Okay. Now what I'll mention is that we are doing this division here. Oh, I missed a step. Yeah. So we calculate this U, this V, and our Z. Well, we can kind of throw the Z away now we've used it. We can use these U corrected and V corrected in our texture. ST space. So we're done. So all that we have to do is do right here. Instead of interpolating the barycentric in object space, we do it in projected space or perspective corrected space. And then we bring it back to object, or on perspective correct it, bring it back. Now we can go back to our texture and we're done. That's it. Now I put a star here. I'll mention that. So this division, this caused all kinds of problems in the past because division for each texel, and remember with shading you might have a whole stack of them with Z buffering and alpha. You know, each one needs this this division. This is expensive. Okay, this division for each texel is expensive, and in the past you'll have seen people try to avoid that by doing it once and interpolating across the shape instead of doing it for each one. Yeah, there are ways to optimize it, but in the end, it's a division. On modern machines, nobody cares, but if you're working on embedded systems or older machines, it's a problem. So let's look at some slides. So we've already seen this slide, and I want to show it again. And now you see all that the difference here is this we have, each triangle has an affine one. This now has the projected, projection corrected mapping, and it looks just as you would expect. The other slide I want to show is a picture here of a classic video game called Doom. In this original video game, which was one of the early first-person shooters, there are a lot of caveats. You couldn't look up, you couldn't look down, okay? And you couldn't look up, you couldn't look down. Doors wouldn't open out, they'd slide sideways. The reason that they did this was to optimize for affine type texture mapping. Now, as you can see, this isn't affine, but they have a lot of constraints put in that would let them interpolate and have a lot fewer divisions than in the general case. If they let you look up, suddenly their interpolations broke. So this was a game that was highly limited by trying to avoid those kinds of divisions. So that's it. So affine perspective corrected texture mapping is not that hard. It just takes a little bit of math. And at the end, if you understand what's happening in the spaces, it's actually quite easy to code up.